the invitation and this introduction. So my talk will be mostly classical algebraic topology based on common work with Martin Palmer and Awais Shaukat. But in the end, I will announce the independent new result by Marco de Renzi and Jules Martel. We are waiting for the preprint, but it should come soon. And an ongoing project with Anna and these two young people. And the slogan will be, that was algebraic topology, but indeed, this should be quantum. So my motivation one accounts for these classical braid groups of an ordered configuration in the disk. And it was shown by Bigelow and Kramer independently. That was 2001 and 2. And it was through a representation. So again, I will use this notation many times. These are unordered configuration of points in the disk. If you are work in algebraic geometry, this is a regular part of the Hilbert scheme, but whatever. So this is a braid group. So you have a representation which is non-embedding in the linear group of certain homology of cover of this space. And this cover is a regular cover with group Z2. And this comes from an homomorphism from a Bn to Z2, which is surjective. And here, this covering space is associated with, of course, the kernel of this homomorphism. So we would like, so this Bn is a mapping class group of D2 with which are identity on the boundary. So I take mapping classes which mean different homomorphisms which are identity on boundary up to isotopy. And indeed, the goal is can we get similar result for the mapping class group of surface in higher genus. It's not known, except in genus 2, if this mapping class group are linear. So the idea is to build certain homological representation and possibly use them for this linearity question. And there is a second motivation, which corresponds to this project. Motivation 2 is algebraic topology construction of TQFTs. Indeed, our construction will produce representation of the mapping class groups, and the mapping class group embed in the cobordism. And the question is, are we able to extend this mapping class group representation into a representation of the 2+1 cobordism category? And this would give classical homology, classical algebraic topology models for what should be called the state space with all the actions. So there is some premise of this. In an old paper, I think it was not so much noted, but by Crivelli, Felder, Bieszczerskowski in the 90s, and they get a commuting action of M of sigma J1, SL2, and UQSL2. And in fact, as a representation of UQSL2, this is U adjoint. the representation here is U adjoint. So this was not really used afterwards. Everything went on the quantum algebra side, but we come back to this. And what are our results? So the result are the following. So we get a quotient map from Bn of sigma, which is of course pi1 of the unordered configuration in this. Here sigma will be always with one boundary component. This is easily extended to several boundary components, but non-empty boundary. And something can be done also with closed surfaces. But I will talk here in the case of one boundary. For those who follow Anna's talk, you understand that this is a great situation. So the first result is this surjective homomorphism on the Heisenberg group of sigma, which I will define shortly. This is a z-central extension of the H1 of sigma. It's non-commutative, but it's the more near to be commutative among all non-commutative. And second, we have a twisted action on a certain homology group associated to the, because you have this, of course, you have a kernel, so you have an associated carver, which I will call the Heisenberg carver. And then you have an action, let's say of M of sigma. Here again, because I have one boundary component, I take mapping classes which are identity on the boundary. And this is my action on let's say H star of Cn tilde from the beginning. So here, in fact, it will not be twisted. So maybe I just put in this case, but meaning that it's Z-linear. But here, because, sorry, this should be maybe in yellow. So why twisted? Because I will also use, I will explain this specialization where I put local system, which means that's the representation of the Heisenberg group. And here, sorry, not yet. Here it's a Z bracket H twisted linear. And this this action is here because you have a carver. You have, I will use the right action convention. You have an action on the right by deck transformation, and then this will give this the structure of a Z bracket H module. And with respect to this action, it's a twisted linear. And but we get a twisted representation if we fix the form rho from H to GLV representation, then you can, I will define H star of Cn, I just abbreviate Cn for Cn of sigma, with coefficient in this representation. I will give the algebraic definition of this later. And then you will get a twisted action, meaning that here you have to twist the coefficients. So here you use rho, and here you use FH composed with rho, where this FH is action of a mapping class on H of sigma. You know that a mapping class acts on the homology by symplectic automorphism, and you can you have also a natural automorphism of this H extension I will give. So here you get something which is twisted. For good representation, you get a true native representation. True representation H to V. You get a native, meaning untwisted, action on H star of Cn with this V coefficient I will define. And then we are able to compute. So 1, 2, 3 computation in certain case, and for quantum. I will talk about quantum. Okay. Questions so far? So now I will enter in the details. So, okay, I have something on the board, so I will go on this side now. First, I will define the braid group of surfaces and the Heisenberg homology quotient. So once this surface braid group and Heisenberg homologies, this Cn of sigma equal the set of unordered configuration. So you can define it's pi1, and in this group you can represent in this group loop in the configuration by its graph in the surface times interval. And for me, because I get sigma equals sigma G1 surface, I like to see this as a disk quotiented by the usual identification on boundary, corresponding to a standard world. And I prefer the model where I take the half horizontal plane and with identification on the boundary. And now when I will draw pictures, you should think that you are living on your surface and you see the identification on this wall. For example, here is, so these are for, I mean, the identification are on a line. The further graph, you take times interval corresponding to the time. And now this, for example, you take a configuration of 2 points, which is with your base configuration. And sorry, I encode, like at school, my identification. And then I will take this guy, which comes here, and I call this a pi1 generator, alpha I. Alpha 1, this is alpha 1. And so in general, I have a pi1 generator where you just move the first strand, one strand of your braid corresponding to one base point, which is inside the base configuration. But you have also classical generator, as usual, sigma 1, sigma n minus 1. And for example, the sigma 1 here will just cross these two strands. And they generate, we know a presentation. I'm using a presentation. In fact, in the boundary case, it was given by Paolo Beningeri in 2001 or 2. But in the close, this has been already in the old time given by Scott and revisited by Gonzalez Meneses. So we have a presentation with a whole set of relations. I will not give the whole relation because it's a little bit long, but I will draw one relation which is quite important. The first tentative as a question would be to abelianize. That was the tool in the case of the classical braid group. But Can I get this board? Okay. Oops. Okay, here I'm representing two surface braids. And because I want action on the right, I'm writing the word from the right and from the bottom. Meaning here, you will get sigma 1. I start with sigma 1. Then this guy will be alpha 1. Then again sigma 1, beta 1, and again sigma 1. And this one will be beta 1, sigma 1, and alpha 1. And indeed, if you are used with topology, you can see an isotopy between both. Take your two fingers here, go down, and ask some other people to push this up, and you will get the other picture. So now, the statement is that this guy is equal to this guy. And if you abelianize here, you will force sigma 1 squared to be 1. Meaning that you are losing almost all the information about the fact that you go from homology to configuration. Okay, so, but using this presentation, it's better if I go on here. So, of course, if you look at this, you can guess what happens, that you pay the price of sigma 1. You have a sigma 1 square on one side, and this should correspond to the fact that you interchange alpha 1 and beta 1. And this is exactly what the Heisenberg group is doing. So the proposition is not very hard, is if you do Bn of sigma quotiented by the normal subgroup of commutators, normal subgroup, generated by the commutators with sigma. So so this is just Bn of sigma quotient with forcing sigma 1 to be central. Is the central extension of h equal h1 of sigma equivalent to h of sigma, which is isomorphic. It's isomorphic as an extension. Z times, as a set, Z times h1 of sigma with rule kx ly equal k plus l plus xy, comma x plus y. And indeed, an explicit iso is obtained by sending alpha I to 0 class of alpha I. I will denote EI, this class. Of course, beta I to the same thing. And all sigma I to U equal 1, 0. So you check that this phi satisfies the relation, is well defined on the group, and you check the kernel. And the kernel is exactly commutators normally generated by commutators with sigma 1. Okay, so from this now, is it okay on the other board? So we have an Heisenberg cover, Cn tilde of sigma, okay, which correspond to the normal subgroup generated by commutator with sigma 1. So now, if you take f from sigma to sigma nomeomorphism. For technical reasons, so I could ask identity on the boundary. I ask identity on a color of the boundary. And I suppose that this color contains the base configuration. So then it's clear that you have a Cn of f from Cn of sigma to itself. You act on endpoints subsets. And then the P1 of this on the kernel of phi is included, in fact, is equal to the kernel of phi. Meaning that you have a lift Cn tilde of f from Cn of sigma to itself. And for free, you get an homological action star to h star of this guy to h star of this guy. Okay, so this, of course, extends to a representation of the mapping class group. But it's probably on a very big space, and we do not completely understand this from this point of view. But we have an action which is linear.
So are supposed to be tildes on the right-hand side? C and tilde sigma, C and tilde sigma?
Sorry?
For the lift, are the
sorry, sure. Thank you so much. So it's Z linear, and it's if you take here, you like to see what happens with the deck transformation action. It will be twisted. So if you take, let's say, Z a cycle, whatever it is, and H in H, then you will send ZH to, because if it's a cycle, so you take U complex, you apply on Cn tilde of F, and then you apply on Z. But here, you will move the H. So you are, this is what we mean by this transformation. So I will say something about this FH. So remember that we started with Bn of sigma. So then here you have the pi1 blah blah, which is acting here. Then you project by phi, you go on H. Here you can go still on H, equal H1. Here you have F star. And here you can show that there is an automorphism FH, which makes the square commute. And this FH belongs to the automorphism of the H group. I will denote with a plus. So plus is for identity action on center. And indeed, because FH is identity in the color of the neighborhood, it acts by trivially on sigma 1, which generates the center. Okay, so now we go one step further. We will use questions so far. So again, we started with the break-root of surface and get a nice quotient group. We take the cover of this corresponding to this quotient group. It's a regular cover. So it has an action by deck transformation on the right in my convention. And then we indeed check that we have an homological action on the homology of the covering space. And it is twisted linear with respect to the Heisenberg action. So now we go to what I consider this one. Maybe it's better to take the other one first. So far, it's elementary. It will stay elementary, but now I will take a row. I will go to what I like to call local coefficient. This is local coefficient. I take a representation onto a certain vector space of my Heisenberg group of the sigma I do not note. Then we get, so we build C, the complex C star of Cn with coefficient in this representation. And this guy is defined as C star of Cn tilde. Here you can use either the singular complex or the cell complex if you understand about the cell decomposition of the configuration, which up to homotopy I can do. So in fact, if you want, you can put here a complex which is a finite rank over the Heisenberg group algebra. But you tensor product with V over the group algebra of Heisenberg, and here you act by deck transformation, and here you act by rho. And now with this, you get H star of Cn with V to be H of this complex. And the question is, what happens with the mapping class action here? And then this is something not very deep. We'll not give the detail, but honestly, it's not very hard. What you get is an homological map. In fact, the idea is that the mapping class will twist the local system. So the native action is not by an automorphism, but it's by an isomorphism between two equivalent local systems. And in formula, this read from H star of Cn with a twisted V to H star of Cn with the native V. And here, I will denote V tau for V with representation, so Fh composed with rho, with growth from H to GL of V equal GL of V2. This is the twisted representation. You pre-compose with an automorphism of the group. And in fact, you can put this together, and a fancy way of formulating a twisted representation is to define a category, which is called the action groupoid, where the objects are the automorphism of H, and the morphism are the compatible mapping classes. So what we get here is indeed, if you do not understand, you can forget, a representation of the action groupoid, which is the category. So now, untwisted. So the idea is, in good cases, the representation V tau is not, it can be isomorphic to V as a representation of H. And then, if this is the case, you will have between this and this an isomorphism coming from the coefficient. If you replace a system of coefficient by an isomorphic one, you will get an isomorphism of homology, which just comes from the isomorphism of coefficient. And then, even in very good cases, you will get this canonically. That you have this, of course, then we do H star of Cn with coefficient V to H star of Cn with coefficient V Fh to H star of Cn with the coefficient, you compose, you get now an automorphism, and here it's iso of coefficient, and here it's homological iso. And then you get an automorphism, and you expect, if you can choose coherently the iso of coefficients, that you get a native representation. And there are good and very good examples. So first, a very good example. Okay. So first, a very good example. And we didn't find this very good example at the beginning, but the idea is rather stupid. So you consider the left regular action. So you take H0 in H, and you take the left regular action, which goes from H to H, and which send H to H0H. What happens is that, so the question is, where does this live? And in fact, if you take, in my form, we understand, I have K prime, let's say K plus K dot plus X0 times X. Now I'm writing H0 equal K0 X0, H equal Kx, and I write the left regular action. And this will give X plus X0. Indeed, if I put the obvious affine structure on H, I mean from the fact that it is Z to J plus 1, I get an affine automorphism. And then I will call L, which will be a Z to G plus 2 equal H plus a summand, the linearization. And then this means that you add an extra, and here you put a T, and it's linear now. So the linearized left regular action is a representation of Heisenberg. And you can think about it, but it is canonical. The twisted is canonically isomorphic just using the tau. If you do here, L tau is isomorphic to L canonically. Indeed, if you take LH0 applied on, L2 of H0, so this will be the affine version of the twisted representation. So this is tau H0 times H. This is tau H0 times tau minus 1 H. And this exactly says that tau intertwines the representation. And this will be the same at the linearized level. So then the theorem from this is that we get a representation of a class group M of sigma to GL of H star of Cn, and it's a native representation obtained by composing the canonical isomorphism of coefficient with the homological action. Then a unitary one. And I think because we like that we like this kind of structure on the state spaces, this is the good direction. So what we know by the theorem, there is this Stoll theorem from Stone and von Neumann, which is HR as a unique, irreducible, unitary. This is a real version of Heisenberg. Okay, so it contains, of course, the discrete version, unitary representation, and this representation I denote W, that it's you have a model with L2 of RG. The construction is well known. Don't know the theory because I will have a more accessible small model. But then this means that in this case, W2 twisted will be isomorphic with W, but because here we do not, this isomorphics will be fixed up to a unitary coefficient, up to S1. So this is, so it's defined up to S1. This means that will be a projective ambiguity when we try to check that it is a representation. But nevertheless, from this, we get a representation, an homomorphism from M of sigma to P U of H star of Cn with coefficient in this Schrödinger representation. This is called Schrödinger representation. And of course, you can feel here that it has something quantum. And this means that you can solve this. This is a classical thing that when you have a projective representation, you get a linear representation of a central extension. So indeed, we can produce a unitary representation of a central extension. And this central extension here is what we call the universal central extension, meaning this has a meaning for genus G for greater than 4. But of course, when you have something in big genus, you can restrict. And this universal central extension in small genus is just the restriction of the universal one with big genus. And we understand, in fact, also the cocycle. So now, sorry, we also have this. Okay, maybe I think I missed something. Here it's with fixed generic central character. Now, the central character is the character corresponding to the central generator. So this is unique up to fixing the character on the center. And in fact, this unicity theorem holds over R, but if you take the discrete Heisenberg, then you have also characters of finite order. So in the case, so we have, check the time, finite dimensional Schrödinger. Here you have to distinguish if the order of the central character is odd or even. So let's say fix P odd, but we can also, this is just to have only one statement. So in this case, consider a central character of H. So in fact, it's U done, give to zeta, zeta P equal 1. We only have order 1, order P. Then we can do HP, which is a question of H. And this is ZP, Z over P, plus H1 of sigma with ZP coefficient. And this has order to P to G plus 1. And here, if you fix Lagrangian, well, Lagrangian will have order P G. So it's a maximal subspace where the intersection form is 0. You take the thing generated by the AI basis. Then you have a one, you take this character and you extend trivially to this Lagrangian. So we have C zeta, which is a one-dimensional representation of centers, meaning Z, P, plus L included in H, a subgroup. Then you can do induction, of course. Then you build W of L equal C CH tensor this C zeta over H, or ZH. And this will give you irreducible representation of dimension P to the G. You get, I mean, this is induction for finite group. And this will have the same role as the original Schrödinger representation. This is a baby equivalent of Schrödinger representation. And then here we have also same result. So now, briefly, I will state what we can do more. First, we are able to compute a variant H star of Cn minus. So there are two variations. One variation is that we consider Borel-Moore homology, and this Borel-Moore homology is the limit with respect to the compact subspace. It's like locally finite chains. So there is a variant which is isomorphic to a sum of 2G. And this relative variant means that we take configuration which has at least one point on part of the boundary. I have no time to say, but it's not very difficult. And this one we can compute, and it's free over, it's finite dimensional, if in case W is finite dimensional, and it's free with finite rank over the Heisenberg group. And next, so this guy, de Renzi and Martel, proves that in the case WP theorem, you have commuting action of UQSL2 at root at pivot, the small quantum group, and mapping class group of an extension, as usual, of sigma on the variant, on a submodule of variant. This one, Cn minus, so the Borel-Moore version with a relative version with WP. And as a space with commuting representation, these can be isomorphic to the power, the G power of the adjoint representation. And this is isomorphic to U adjoint tensor J with respect to UQSL2 action and M of sigma action, because these spaces are the TQFT spaces constructed in the non-semi-simple TQFT. Okay, so again, we constructed homology of configuration with this subtlety of local coefficient. It's not clear that we can compute the absolute version. I have a model, but it's not computed. But we can arrange a version which is relative to part of the boundary and infinity, which we can compute. And this guy is nice in the sense that if you take in genus 1, you recover the adjoint representation of the small quantum SL2. In fact, here, I'm sorry, it's the sum over n of the Hn, and the E action, the F action will add 1 point, and the F action will reduce 1 point. So you need to take the sum. Each Hn will be a weight space of the adjoint representation. And so now the question is, because we recover a TQFT model, we know that in certain case, you do not have only action of mapping classes, but action of the cobordism. And we expect that this action of cobordism could be obtained in a situation with other more general representation. And we have a picture for this action, but it's not done yet. It's a ongoing project. Thank you.
We have some questions for Christian. Maybe I can ask them. Anna Azat has a question.
Yeah. In the picture of Lubashenko mapping class representations, right? We have similar situations.
Yeah, this is. You recover.
So you think this recovers Lubashenko mapping class representations?
Yeah, because there is, sorry, I should say Lubashenko. Originally, these are the representation of Lubashenko, but they were extended to the non-semi-simple TQFT and the space of Lubashenko and the TQFT space in the case where the surface has one boundary component are isomorphic as a representation.
This I know, yeah, but this particular action, it's equivalent to that one, right?
Yes.
Okay.
Yes. This is the result which will come of Martel and the Renzi. They are checking in the basis the formula, so it takes some time. There should be, it could be a more conceptual thing, but this is on the way. This would come. This is not published, but checked. I was allowed to announce the result and to make some publicity for the work.
Okay, so I had a very naive question. This finite dimensional Schrödinger picture, do you know if there's any relation to what physicists do when they talk about sort of quantum mechanics and characteristic P or
it has
anything like that?
Yeah, it's connected with the. At least I don't know if this answers your question, but it's connected with the U1 TQFT, if you want.
Yeah.
And to in algebraic geometry to representation of what they call theta functions. So I don't know if this is connected, but it's likely. Yeah, but here you see that this is you have two steps. First, you have the step at the level of this representation and the local system. So in fact, what you have is a functor from the surfaces together with a representation of this Heisenberg to a certain category of module of Heisenberg. And this is coherent with the mapping classes, and we expect coherent with also the cobordism. And the second step is to understand, once you fix the local system, what is the homological action. And we have, I mean, the first step is rather well we are understanding. The second step needs still some work. What we expect at the end of the day to have a complete homological model for this TQFT front-end.
Last chance for questions. If not, we thank Christian for his fine talk.
I know we have a speakers in this morning's session. Thank you.